Welcome to the Explainer. Today we're zooming in on Earth's most abundant yet entirely bizarre chemical anomaly. We all think we know water, right? But as we strip back the layers to look at its quantum geometry, you're going to realize just how strange H2O actually is.
So, I want to pose this question directly to you to kick things off. Is water the weirdest substance on Earth? Seriously, it covers 71% of our planet. It's literally the foundation of all biological life, yet it completely ignores and outright breaks almost every standard rule of chemistry. To figure out why, well, we have to look at the data.
Okay, let's dive into this because this fact is absolutely mind-blowing. If you look at chemical compounds that are structurally similar to water, their physical properties dictate that water should melt at -90 degrees Celsius and it should boil at -68 degrees. But look at the actual numbers. It doesn't boil until it hits a scorching 100 degrees Celsius. That is a massive 168-degree gap between expectation and reality. By all normal scientific logic, the water sitting in your glass right now, it should be a gas. So, why isn't it?
Section 1. Anatomy of a water molecule.
To answer why water is such a rule breaker, we need to examine the internal machinery of a single water molecule. Here we have our classic H2O, one oxygen atom, two hydrogen atoms. Now to reach stability, these atoms share their electrons to fill their outer energy rings. This creates what's called a covalent bond, and it's incredibly strong. But here's the catch. They don't share equally. The oxygen atom is highly electronegative, which basically means it's a huge electron hog. Because the electrons spend way more of their time just hanging around the oxygen atom, it creates this magnetic-like polarity. One end becomes negatively charged, and the other becomes positively charged.
And this polarity, it creates a very specific, absolutely crucial geometric angle between the two hydrogen atoms, exactly 105 degrees. I want you to lock this number in your head, 105 degrees. It is quite literally the secret mathematical key to water's superpowers.
Section 2. The universal solvent.
Let's see how that 105-degree polarity allows water to interact with, well, pretty much everything else out there. Because of that polarity, water molecules are incredibly social. The negatively charged oxygen of one molecule acts like a magnet, snapping onto the positively charged hydrogen of another. We call this connection a hydrogen bond. Now sure, these hydrogen bonds are weaker than the covalent bonds holding the individual atoms together, but they are absolutely strong enough to connect water molecules to each other in this constantly forming, breaking, and shifting dynamic web.
And you can see exactly what happens when you introduce something else into that web. This is water acting as the ultimate universal solvent. When you drop everyday table salt into water, the water molecules essentially gang up on it. The positive sides of the water surround the negative chloride ions, and the negative sides surround the positive sodium ions. This process, known as hydration, makes the sodium and chloride ions 80 times less attracted to each other. Water literally and, kind of violently rips the solid salt apart just by surrounding it.
Section 3. Defying the rules of heat.
So we've seen the microscopic structure, but what happens when you expose this vast web of hydrogen bonds to heat? Well, it creates some massive physical anomalies. When we measure specific heat capacity, which is just the amount of energy it takes to raise the temperature of 1 gram of a substance by 1 degree Celsius, water sits at a flat 1.0. Compare that to wet mud at 0.6 or iron way down at 0.11. Because those hydrogen bonds take so much energy to break, water requires a significantly larger injection of heat just to get its temperature to rise compared to something like earth or metal.
And this translates directly into those massive melting and boiling point anomalies we touched on earlier. Again, structurally similar chemical compounds without hydrogen bonds melt at -90 and boil at -68. But water, the sheer amount of energy required to break that hydrogen web, is the only reason our oceans aren't boiling clouds of gas right now.
The real kicker here is understanding latent heat. Let's say you have a pot of water already at a rolling boil, 100 degrees Celsius, and you want to turn just 1 single gram of that liquid into a gas. It requires an additional 540 calories of heat energy. And get this, adding all that extra energy doesn't even raise the temperature of the water vapor. No, all 540 calories are completely consumed just breaking the hydrogen bonds to set those molecules free. It's wild.
Section 4. Earth's global thermostat. When you step back from the microscopic view and apply these incredible thermal properties to the entire Earth, you suddenly see the mechanics of a global thermostat at work. What we're really looking at here is a massive thermal engine. Down at the equator, the sun beats down, pumping huge amounts of heat energy into the ocean. But instead of making the water boiling hot, that energy is absorbed as latent heat to evaporate the water. This vapor then travels through the atmosphere up to higher, cooler latitudes, where it condenses back into rain, releasing all that stored heat back into the environment. It is essentially a giant planetary air conditioning system, constantly moving surplus heat away from the tropics.
And you can see this buffering effect perfectly when looking at global temperature swings between day and night. Notice how the vast oceans barely change temperature at all. But then, look at the dry land masses, where the temperature violently swings from scorching hot during the day to freezing cold at night.
To put this into perspective for your everyday life, if you live in a coastal region, your mild weather, those cool summer breezes, your warmer winters, they are a direct result of the ocean absorbing and slowly releasing heat. But if you head inland, where rock and soil have a super low heat capacity, you face drastic extremes. Basically, your perfect beach day is mathematically powered by the water molecule's unique ability to absorb heat.
Section 5. Why ice floats? For our final section, we're going to look at water's ultimate party trick. It's the final anomaly, and it happens when temperatures drop below freezing. You see, most substances in the universe follow a very simple rule. As they cool down, they lose kinetic energy, their molecules pack closer together, and they get denser. Solid lead is denser than liquid lead. But let's track water. It cools down, it packs tighter, it gets denser, right until it hits exactly 4 degrees Celsius. At 4 degrees, water just stops shrinking. As it continues to cool towards zero, it suddenly does the unthinkable. It expands. And this beautifully illustrates why that happens. Remember that 105-degree angle? Well, when water drops to 0 degrees, the molecules lock into a solid ice crystal lattice. But to form this rigid structure, that angle physically has to widen from 105 degrees to 109 degrees. This widening forcefully pushes the water molecules further apart. As a result, the solid state is actually less dense than the liquid state. Ice floats. If ice sank, our oceans would freeze from the bottom up, killing all marine life and turning Earth into a giant, uninhabitable ice cube.
Which leaves us with this final thought. The only reason our climate is stable, the only reason life can exist in the oceans, the only reason we are literally here is because of a microscopic angle of exactly 105 degrees. It really makes you wonder, right? If this tiny piece of atomic math creates the macroscopic magic of our entire world, what other invisible geometries are secretly shaping our universe? Thanks for joining me on this explainer. Until next time, keep exploring.